everyone, welcome to today's class. In today's class we are going to learn about the gas cycles. Let's say we have Otto cycle, diesel cycle, dual combustion cycle as well as Brayton cycle. In today's class we are going to deal about what are the comparison between the Otto cycle and the diesel cycle. Let's see. First, in Otto cycle, the processes involved in Otto cycle 1 to 2. What is 1 to 2? It is nothing but adiabatic compression process. Adiabatic compression process. 2 to 3 is constant volume heat addition. Let's say 2 years heat supply, that is heat addition process. And 3 to 4 it is adiabatic expansion process. Adiabatic expansion process. And 4 to 1 this is also constant volume heat rejection process. So the processes involved in Otto cycle are adiabatic compression, constant volume heat addition, adiabatic expansion, and the constant volume heat rejection. The same way we are going to look at the process involved in diesel cycle. Okay, in diesel cycle, so 1 to 2. So here it is adiabatic compression. Here the diesel cycle, the 1 to 2 process is also adiabatic compression process. Okay, adiabatic compression process. And 2 to 3 is constant volume heat addition process. But here it is constant pressure. It is constant pressure heat addition process. In 3 to 4, here it is adiabatic expansion in Otto cycle. In diesel cycle, this is these are the adiabatic expansion. The same process here also reflected. Adiabatic expansion. So there is no deviation. And 4 to 1, this is constant volume heat rejection process. In diesel cycle it is also same thing, constant volume heat rejection process. Okay. Once again, process wise we have compared in Otto cycle and diesel cycle. All the processes are same. Only the difference in processes is in the constant volume heat addition. So just note down here, heat addition takes place constant volume. That means we are keeping or we are treating the volume as constant. But in diesel cycle, the heat constant, there is a heat addition process takes place under constant pressure. Instead of the volume to be making constant, the pressure to be kept constant in the diesel cycle. Other processes are same, but there are some deviation in finding the efficiency of the Otto cycle as well as diesel cycle. Okay. Then let's move on to the efficiency. Move on to the efficiency point of view. Just draw the PV-TS diagram. Draw the PV-TS diagram. So PV diagram for Otto cycle. This is a pressure, this is volume. Okay. Here 1 to 2 is adiabatic compression process. The point 1, here point 2. In between during the adiabatic compression, the pressure is increasing. So here the pressure is rising, at the same time volume gets decreased. So 1 to 2 process. Then the 2 to 3 process is constant volume heat addition process. During heat addition, what happens? heat added, temperature gets increased so that the pressure will be increased. Okay, the pressure will be rise. So here the volume is maintained constant. So it is a vertical line. So this is 2 to 3. In 3 to 4, it is adiabatic expansion. Adiabatic expansion expanded. So volume gets increased. Okay, volume gets increased. The same thing, the pressure gets decreased. So it is in the manner of going down. Okay. So this is adiabatic expansion. 3 to 4. Finally, we have constant volume heat rejection. So temperature drops down, so that the pressure also drops down under constant volume. So it should be a straight line. Okay, so 4 to 1. So here you have a heat rejection. Here you have a heat addition. Here 1 to 2 is adiabatic compression process. Okay. So diesel cycle, we are going to deal with only PV diagram. Okay. Saying pressure versus volume diagram. So here we have adiabatic compression. So pressure increasing 1 to 2 will stay. In 2 to 3, what happens? The pressure under constant pressure, the heat is added. Okay, so the heat is added under constant pressure. So pressure is maintained constant. So 2 to 3. So here we have added the heat. And 3 to 4, we have adiabatic expansion. So volume gets increasing and pressure also increasing. Finally, you have a 4 to 1 is constant volume heat rejection. So constant volume get constant. Okay, and the temperature drops down. So it's a closed cycle. So point 1 should be constant here. So you have to just extend this. Can draw this. So this is 1 to 2 for adiabatic compression. This is adiabatic expansion. This is a constant volume heat rejection 4 to 1, the constant pressure heat addition. So this is the comparison with respect to the PV diagram between the Otto cycle and the diesel cycle. Okay. Finally, we can have the efficiency. So I will give you the final derived efficiency formula here for both Otto cycle and the diesel cycle. Let's take efficiency, Otto cycle efficiency. Takes we take as theta. Okay. So what is the Otto cycle efficiency? It's nothing but 1 minus 1 by RC power gamma minus 1. Okay. So here we have only 2 notations. One is RC and one is gamma. What is RC? So RC is nothing but a compression ratio. So RC is compression ratio. It means how much volume, that is the volume ratio during the adiabatic compression stroke. That is V1 by V2. This is gamma, this is adiabatic X. Okay, this is gamma, this is adiabatic ratio. There is a gamma equal to CV by CV, adiabatic index. Okay. So we have this adiabatic index is depends on the Cp and Cv value with respect to only gases, whether carbon dioxide or air or oxygen. For gases, this is constant. So we don't bother about it. We have to bother only on the compression ratio. So how much volume is increasing from the starting point to the end of the compression stroke, so that the compression ratio will be increasing. If the value is higher, the Otto cycle efficiency is higher. Okay, generally it should be greater than 1. So this point will be less than 1 point. So you have to have a 1 minus 1 value, you get a higher value. Okay, so when RC is higher, the efficiency also higher for Otto cycle. Then we can move on to the diesel cycle. For diesel cycle we can have an expression for diesel cycle. The same thing 1 minus 1 by RC power gamma minus 1 into 1 by gamma. Okay, 1 by gamma into another factor called rho gamma minus 1 by gamma minus 1. Okay, 1 minus this value. Okay, so here we have RC we can have gamma same. One more factor is called rho. Okay, so rho here is cutoff ratio. This is cutoff ratio where the fuel is cut off. That is called the cutoff ratio. So we have a heat addition process. It is in the process number 2 to 3. Okay, one is constant volume heat addition. Here is constant pressure heat addition. Okay, so this is the point at which the fuel is cut off. The point is called cutoff ratio. So the ratio means the volume ratio during the heat addition process. Okay, that is the cutoff ratio. Here the significance is you have a compression ratio. If it is increasing, the efficiency also increasing. Okay, this is one thing here. And another thing is if this cutoff ratio is increasing, efficiency will be going down. Okay, so this is the same thing, vice versa. If cutoff ratio is lesser, efficiency will be higher. Okay, so this is the significant points between the Otto cycle and the diesel cycle, and the efficiency reflects on only on compression ratio in the Otto cycle, and in the diesel cycle both the compression ratio as well as the cutoff ratio, and with respect to the significance I have given the ratio which one is higher, and which reflects on the impact of efficiency also. Okay, I think you will find an easy thing between the comparison of Otto cycle and diesel cycle. I will repeat you the next class with a different topic. Thank you.